All right, I see it's live streamed. Good to go.
Yes, you're
Okay,
live.
so thanks a lot for the invitation and the introduction. So today I'd like to tell you about work that I did over the last 2 years or so with Scott Collier, Beatrix Mühlmann, and Victor Rodriguez. And it's about understanding sort of simple string theories, so these 2D string theories, better. So we all know that the landscape of string vacua, like physically semi-realistic string vacua, is extremely complicated. So I won't try to talk about that. But the situation for 2D target space, so if you take a non-critical string theory with a 2D target space, is much more controlled. And there are sort of two famous classes that have been explored in the literature. One is the so-called minimal string. I'll review what that means. It's labeled by two integers, the PQ minimal string. And it has kind of amazingly, I think, a duality with a matrix integral, so-called double scaled, and you, strictly speaking, need a two matrix integral. And there's sort of a cousin of this is the so-called seek to one string. And it also has a duality, but it works slightly differently. It's dual to not a matrix model, so just an integral over a matrix, but a matrix quantum mechanics. So there's also time in the dual. So both of these are pretty well studied in the literature. I would say this one even more than the seek to one string. And both enjoy dualities similar to the ADS-CFT correspondence. And so natural question is whether this is everything, if there are more sort of 2D string theories, and if they also enjoy these kind of dualities. And so there are some other explored versions of those, but today I'll tell you about the more sort of irrational cousin of these dualities, and it will be fairly close to the duality between the PQ minimal string and a matrix integral. So in particular, there will be still a matrix integral dual to these theories. And I think in some sense they're in some sense simpler than the PQ minimal string. Okay, so the standard paradigm of these two-dimensional string theories is that you take string theory composed of some worldsheet theory. So this is constructed in the usual way. Let me just review how that goes. So you just do bosonic string theory. So a bosonic string is specified by specifying a matter or some worldsheet theory that has central charge 26. And then you couple it to BC ghosts, which is a different way of saying you integrate over all the worldsheet metrics. So you're gauging all the worldsheet diffeomorphisms, and that leads to the introduction of some ghosts. And famously, this whole thing is only consistent when the center charge is 26. So one solution of this is to take 26 free bosons and add the BC ghost that gives the usual bosonic string in 26 flat target space dimensions. We also know this leads to a tachyon, so it's not a good thing to do. But in these two-dimensional string theories, these are tachyon-free. So these are proper sort of string theories. And two-dimensional means, roughly speaking, that the worldsheet theory has two factors describing the two target space dimensions. And one of those factors will always be Liouville conformal field theory. So this is a particular conformal field theory of central charge that you get to choose. So it exists for any central charge. And you couple it to some matter theory. And this matter theory might be a zero-minute model. You might be a free boson. And these two options lead to the PQ minimal string and the seek to one string. So the persistent paradigm is sort of that if you choose something like this, then usually it's dual to some double-scaled two-matrix integral. And those are just integrals over matrices with some measure factors. By the way, I'm not completely sure what the background of everyone in the audience is. So I was told there's some mathematicians, some physicists. But feel very free to speak up and ask about things or say this is all trivial, whatever you think. So I unfortunately cannot be there in person, but hopefully we can still have it a bit interactive. All right. So let me just tell you a little bit how this goes. So the landscape I'll tell you about, roughly speaking, looks like this. So it has different sort of components, and I plotted them in the complex center charge plane of this matter theory. So let's start from the sort of simplest theories. Those are these minimal string theories. And the simplest one you obtain by taking the 2, p minimal string. So before there were 2 integers, and now I'm putting one of these integers to be 2. And this is defined on the worksheet by having a 2, p minimal model for Virasoro. And those are special because these are the sort of the simplest, they're the simplest minimum models. And in particular, those can be described, the special thing about them holographically is that they can be described by a one matrix integral. So this is just an integral over one single matrix. Alternatively, you might also think about it as a two matrix integral, but one of the matrices has a Gaussian potential, so you can just integrate it out. And those have some, so depending what you choose for P, these have some different center charges, and all the center charges are less than one. So you get some discrete set of possibilities here. Those are often also called multi-critical matrix models, and that depends. This P you can define as some in this index of multi-criticality in this matrix models. One feature that has been also explored a lot in the more recent literature is that if you take P to infinity, meaning that you take the center charge of this minimum model to minus infinity, and the corresponding center charge of the Liouville theory to plus infinity, such that the sum is always 26. This theory in some sense simplifies or becomes classical, and it reduces to a simpler duality between a string theory and a matrix model. And you can see if you take this appropriate scaling limit here, this reduces to the sinh of square root of E, and this is the density of states that appears in JT gravity. So the sort of worldsheet theory, if you consider a 2D theory of gravity, meaning you have to integrate over all the metrics on the worldsheet, that's a 2D theory of gravity, is this Jakiv-Teitelbaum gravity that has been studied by Sachenker in Stanford and others. And in particular, all the observables of this 2, p minimal string in this limit will reduce to Wald-Peterson volumes. So these are the volumes of moduli space, which are essentially the observables of this JT gravity. So this has been studied a lot. Slightly less studied, I would say, is this PQ minimal string. If you take both integers to be non-trivial, so they have to be co-prime, but you can take Q to be 3 and P to be 4, say. And in this case, the dual has to be this 2 matrix integral to describe it. And so you get to have much more of these crosses on the real axis. And in particular, this 2 matrix integral is conveniently parameterized by this so-called spectral curve. And it's a way of saying what sort of the branch cut structure is of the simplest observables in this matrix integral, which is a resolvent. I'll get to this a little bit later. So that's one class that has been explored a lot. And then the first generalization of this I want to discuss is where you replace this Virasoro minimum model by so-called time-like Liouville CFT. This sometimes also in the literature is called imaginary Liouville CFT. It's sometimes also called Liouville CFT with center charge less than 1. So this has different names, this theory. And so we are maybe somewhat used to this Liouville CFT of center charge 25. I'll tell you later on exactly what it means. But let me just emphasize that this Liouville theory where center charge is less than 1 is pretty different from this one. So those two theories, they're not analytic continuations of each other or anything like this. So this Liouville theory, you can only define when the center charge is bigger than 1, the usual Liouville theory. And when the center charge is less than 1, it's a completely different theory. There are still some aspects that are similar, but it's not some analytic continuation. But you can couple these two things to each other. And again, couple to BC ghosts and make some critical string theory. And you can again look at the observables. And this, you still find that is dual to a matrix integral. Actually happens to be a 1 matrix integral again. So it's similar to this 2, p cases. But now the density of states takes this form. So before, the density of states for the 2, p minimal string was the sinh of arc posh type of function, and here it's a product of 2 singes. And but we'll see that in some sense this is much simpler than the 2, p minimal string. The corresponding string amplitudes that you can compute in this theory.
Sorry, just terminology. In what sense the string is minimal?
I would call everything minimal that is a bosonic string that doesn't have a tachyon. So typically,
minimal is just absence of tachyon, yeah?
yeah.
So it's
So
basically the central charge of matter is less or equal to less than 1.
yes, that's right.
Mm.
Well, we'll have sort of, okay, I'll revise. So let me say the effective central charge of the matter is less than 1. So the central charge can be bigger, but sort of the effective central charge is the central charge that measures the number of degrees of freedom. And for example, for Liouville theory itself, the central charge is bigger than 25, but only has 1 degree of freedom. And the effective central charge, which is defined as the central charge minus 24 times the minimum conformal weight, that is always 1 for Liouville conformal field theory. And that's the quantity that's relevant to have note that the tachyon is absent. So in particular, the effective central charge of the full worldsheet theory needs to be at most 2. Good. Thanks for the question. Yeah, so this answer was needed for this to make sense. So there's yet another version that we looked into, and then you can tell me if you can come up with even more versions. But one more option that you can do is to just couple 2 Liouville theories to each other. And in particular, you can define Liouville theory for any complex central charge. So in particular, one choice that you can take is that this Liouville theory, the first Liouville theory has this funny imaginary or complex central charge. So the central charge is 13 plus some imaginary number. And the second Liouville theory has the central charge, the complex conjugated central charge. So 13 minus that imaginary number. I'm restricting mostly to this real part, the 13 case, because in this case, there is still a non-unitary inner product in the worldsheet. Otherwise, you cannot even define a sesquilinear form in the worldsheet. But in any case, if you have this theory, it turns out that it's still dual to a double-scaled matrix integral. This time is a 2-matrix integral. And it has, again, a spectral curve, which looks like this. And for those familiar with the minimal string, this might look very similar to the minimal string. But this B parameter here is complex, and that makes the structure of the spectral curve quite different. And here you can compute again string amplitudes that we'll discuss later on. In particular, all these string amplitudes, once you know that there's a matrix integral, they can be computed by a recursive procedure that is known as loop equations or topological recursion, depending if you ask physicists or mathematicians. All right, so that's the rough overview, what we will talk about. So I'll explain you these new dualities and where they come from and why I think they're nice and how in some sense you can derive them directly. One thing that I already want to emphasize is that in this PQ minimal string, there are some subtleties because these integrals that you try to compute over modular space are not always convergent. This does not happen for these irrational cousins. So you have fully convergent integrals over modular space. And so in particular, all these string amplitudes that you're computing, they will be analytic and kind of simple functions. Whereas in the minimal string, the functions that you're getting for the string amplitudes, they often have some case distinctions depending on in what ranges you use it. All right. Any questions at this point? Great. So let's get started with this string theory, which we call the Virasoro minimal string, for reasons that hopefully will become more clear in a bit. And let's recall that it was defined in this way. So we take this central charge bigger than 25, the just ordinary Liouville conformal field theory, and we couple it to this funny time-like Liouville conformal field theory. And if you define the central charge of this guy to be 26 minus that, you get a critical worldsheet theory. Okay, so let me tell you a little bit about the ingredients. So maybe some of you are very familiar with this. So what is Liouville conformal field theory? It's a particular solution to the CFT crossing equations. It's a non-compact theory, by which I mean it has a continuous spectrum and is unitary. And it was constructed, first Dorn, Otto, and Zamenhof squared, derived the 3-point functions. There was a sort of a bootstrap type of derivation by Teschner. And then more recently, mathematicians also constructed this theory more rigorously using probabilistic methods. So it's convenient in this theory. So this theory exists for any central charge. I'll take the central charge to be bigger than 25. You can extend that a little bit further, but we won't need it. And there's a standard parameterization of the central charge in terms of another parameter b. So it's just often much more convenient to write things in terms of this parameter b than instead of c. And the condition that the central charge is bigger than 25 corresponds to b being real. Good. And the theory has a very simple spectrum of Virasoro primaries. And all these Virasoro primaries are spinless. So h is equal to h bar. And their conformal weight is continuous. So there's a continuous series of these primary operators, and it's bounded from below. And it's bounded from below by c minus 1 over 24, which is bigger than 1. So this just maybe to come back to the earlier question, the vacuum is not part of the spectrum. This is also why sort of in the high energy regime, we usually have Cardi growth, but this theory has a Cardi growth only of central charge 1, because there's the lowest state in the theory is not a vacuum. And the sort of amazing thing about this theory is that the OPE data is completely known. So there's a closed form expression for the 3-point function of 3 primary vertex operators, which is given by this DOZZ formula after the initials of these people. And once you know this DOZZ formula, you can compute in principle any observable in the theory by doing conformal block expansion. So let's say you want to compute a 2-point function on this genus 2 surface. Then what you need to do is you need to define a conformal block expansion, which corresponds to chopping up the surface in pair of pans, inserting a 3-point function for every pair of pans that you find, integrating over all the intermediate momenta that you inserted, multiplying with conformal blocks, and before integrating, and that's your answer. So in principle, once you know the 3-point function, everything is specified. You can repeat the same game with this time-lag Liouville conformal field theory. That's also a solution to the CFT crossing equations. It's also non-compact, so it also has continuous spectrum, but it's not unitary because the central charge is less than 1. And similarly, it was, its literature is a bit more modern. So it was first pointed out by Zamolodchikov. I think that there's another solution to this bootstrap procedure of Teschner. And then sort of the meaning was further elaborated in these papers, and also more recently it was rigorously mathematically constructed. As I mentioned before, it's not the analytic continuation of ordinary Liouville theory to this new regime where the central charge is less than 1. It's still convenient to parameterize the central charge in this kind of way. It's the same as before, it's just some minus signs are slightly different. So before there was a plus and a plus here. So in particular, you go from one formula to the other by replacing B by IB. The spectrum is exactly the same. So it's also bounded from below. But now notice that this bounded from below starts below the vacuum because C hat is less than 1. But there are states in the theory with negative conformal dimension. And finally, there's a solution for the 3-point function. And the solution is essentially 1 over the space like the ordinary Liouville answer. So that's a bit funny. The structure constant is really inverse. And it's the inverse, it's the structure constant of space like Liouville theory where every momentum is replaced by I times the momentum also. So you can show that this also satisfies crossing. There are some subtleties. If you compute the 4-point function, this has a bunch of poles and you have to be a little bit careful with the contour you're integrating over. But let me not dwell on this too much. And again, you can compute any correlation functions of local operators via conformal block expansion. You can kind of already see that this will lead to something nice once we combine the theories, because the one 3-point function, roughly speaking, is the inverse of the other 3-point function. So many things will tend to cancel out between these theories. So even though the ingredients are pretty complicated, they involve this DOZZ formula, which is quite complicated. Once you put them together, things tend to simplify a lot. So let's see how we put that together. So we want to compute these string theory observables. in particular, the condition that C hat is 26 minus C is just translates into the fact that this B hat parameterizing the central charge of the time-like Liouville theory is equal to B of the Liouville theory. And similarly, in string theory, if we have vertex operators, we need to satisfy the mass check condition. Means that the total conformal weight has to be equal to 1. That translates into the fact that this Liouville momentum, the time-like Liouville momentum, is I times the space-like Liouville momentum. And so on-shell vertex operators are very neat, I think. So they're just given by the vertex operator on the Liouville side times the one on the time-like Liouville side, where you replace P by IP. And then if you take the unintegrated version, you also multiply by these C-goes. But let's not worry about those. So you can now define your string theory observables, which are just given by taking Liouville correlation function times this time-like Liouville correlation function times the appropriate ghost factors, and then you can integrate this over the modular space of surfaces. And this will give you some function depending on G, of course, and N, as well as the central charge that you picked, which is described by this B parameter, and all the P's that go into here. And maybe also, you could have thought you can also do more complicated vertex operators involving descendants and so on. But the only non-trivial BRST cohomology, or the only non-trivial vertex operators, are operators that are primary times primary. Or, well, you can find more complicated equivalent representations of that, but there are no other non-trivial vertex operators in this theory. So that would be also one definition of minimal. The two are the same.
Sarah, is there any analog of this ground ring?
Not in this. There is one that is complex Liouville string. In the other one, there will be. But here, I don't know of. I don't know of any. I would love to know. The main problem is why this ground ring doesn't. The ground ring construction works because there are degenerate vertex operators in the theory. And time-like Liouville.
Here you excluded all of them, yeah?
Yeah, but so in time-like Liouville theory doesn't naturally have any determinate vertex operators. That's why I don't know how to construct this ground ring. In this Liouville times Liouville, this what I call complex Liouville string, I know how to do it. I can talk about it later if you want.
Thank you.
Great. Any other questions? Okay. Right. So. And let me point out, I mentioned it already at the beginning, that these are absolutely convergent integrals. So as long as you take this P to be real, which is the usual spectrum, then this integral converges absolutely. And we're calling them quantum volumes, these amplitudes, if you want, because they will turn out to be deformations of the Wright-Peterson volume obtained in a precise way by quantization. So let me explain how that goes. And in particular, that gives a sort of derivation for what the matrix module is. It's not completely rigorous. So that's why I put this exclamation mark here. So if you're mathematicians, you have to take a leap of faith. So you can think of this theory in a very different way. Namely, you can think of it as coming from 3D gravity. How does it work? So it works by noticing that if you have conformal blocks, Virasoro conformal blocks, then you can define an inner product on the space of all Virasoro conformal blocks. And this inner product looks like this. So you take two conformal blocks, and sort of if there are external punctures, then I'll assume that these external punctures satisfy the mass check condition, but internal labels, internal momenta can be different. So these will be functions of the moduli, the conformal blocks. Just think of a four-punctured sphere one. And so I can take one conformal block times the other conformal block complex conjugated. And then this is almost like a conformal field theory partition function, whose center charge is the center charge of the conformal block. So I can repeat the same of what I did on the previous slide. I multiply this by a time-like Liouville correlation function. so that everything becomes on shell here. This becomes like a string amplitude, and the center charge becomes 26. I couple it also to BC ghosts, and then I integrate it over the modular space. There's only one slight thing that I'm doing wrong that's important, is that just a single conformal block is not crossing symmetric on its own. It's not a solution to the CFT crossing equations. So that means I cannot integrate it over the modular space of Riemann surfaces. Instead, I have to integrate it over the covering, the universal covering of this modular space, which is known as tight mirror space. But once I integrate over this larger space, then this integral is well defined. And in fact, this integral is very simple to evaluate. This integral is always proportional to delta function, which you can kind of easily see because a part of this integral here involves integrating over Dean twists, and integrating over the Dean twists gives you delta function at p is equal to p prime. And in fact, you can figure out what the sort of correct measure is on the right-hand side with this delta function by noticing that this conformal block is defined such that if you perform joint crossing transformations on both conformal blocks, this inner product is unitary. So this inner product makes all crossing transformations unitary. If you use this constraint, you can bootstrap what this density has to be, and you figure out that it's just the sort of OPE density of Liouville conformal field theory, which means this for every place in your pair of pants decomposition where you cut, you get a density of states, and every 3-punctured sphere you get a structure constant. This is just a DOZZ formula.
Sorry, can I ask a question?
Yes, please.
Can you hear me all right? Yeah, okay. So what I wanted to ask is, you're saying that this final answer is basically determined by properties under crossing transformations of the
Yes, that's right.
of this object, and where exactly do we use the fact that under the integral we have the correlation function in time-like Liouville theory? Can we instead have like some other correlator in theory, same like central charge? For example, you could imagine a different definition of this inner product using like minimal model.
Yeah, very good question. So you can write minimal model here, and you will get some kind of modified conformal block, which only exists for some discrete set of centered charges, right? Because minimal model only exists for this discrete centered charge. So in the bootstrap of this function here, you're using that the answer is continuous in B and also analytic in P, which you know that is satisfied by the integrand. And you also know that, so it's also important to put time-like Liouville theory here such that the integral converges. So you're right, you can put the minimum model and you will get some different answer, but, which I don't know how to compute because it violates this continuity assumption in B. If you put some completely random theory, then typically the integral will not converge. And then you also get into trouble. So, but you're not explicitly using it in some sense, you're only using its property. But this Liouville theory in some sense is unique. So, yeah.
I also have kind of similar question. Why, sorry, why this formula doesn't work other way around? So if you multiply to time-like blocks and integrate it with the Liouville correlation function.
That's a good question. I think it does work. The only trouble that I have is that I don't know. Yeah, so it might work. So the obstacle is that I don't know the crossing properties of conformal blocks less than 1 and with center charge less than 1. So crossing properties are only known of conformal blocks with center charges bigger than 1. And the corresponding crossing kernel does not work when the center charge is less than 1. And there have been attempts in the literature to rectify this, and there's a recent proposal for how to do it, Roussillon. But yeah, that was after we wrote the paper, and it looks much more complicated than for the space-like case. But I'm not excluding that there's a similar form.
I see.
Sarah, and what do you mean about the derivation of matrix model? Who is here is
Yeah,
this
so this will be in the next slide. So
next also. So this row is
so
not.
this is something that is completely different, or looks maybe completely different. But
So I should not think that this your row in the measure is somehow related with density of states in matrix model.
Yes, it will be.
It
Yeah.
will be, but
Yes.
only for this theory. For example, these simple results for minimal model coupled to gravity of this GT gravity, as you say, they cannot be the densities cannot be derived in this way.
JT gravity, yes, because JT gravity turns out to be a limit also of this Virasoro minimal string. So you can just take a limit in case of this. For minimal model, I don't know. There's a proposal by Artemev how to like more geometrically understand it, but I don't think it's completely understood. And the trouble is often that you're facing non-convergent integrals, so you have to think carefully in what space you're doing that or what regularization procedure you're doing.
Thank you.
Great. Yeah, let me go to the next slide then. The idea is just that once you know this integral, you know an integral that is very similar to the integral that you want to compute. Namely, you want to compute the integral over a moduli space, but not of single conformal block, but of the Liouville correlation function. So you can notice this very formal, formal equation. So maybe one can make this more rigorous, but so the number. So if you want to know what sort of the number of conformal blocks is, well, of course the number of conformal blocks is infinite, but I only want to know the number of conformal blocks up to that combinations of conformal blocks that are invariant under the mapping class group. So more formally, what I mean is I take the dimension of the Hilbert space and I divide it by the order of the mapping class group. So of course, both the order of the mapping class group, which is the set of all crossing transformations, and the dimension of the Hilbert space are infinite because this Hilbert space is labeled by the internal Liouville momentum. But you can do the following formal manipulation and you get something finite. So if you take the trace of the identity, you get the dimension of the Hilbert space, and you can write the identity by inserting a complete set of states like this. And here I'm using that the inner product between two of these things is basically 1 over this density rho times a delta function. So these is an orthogonal basis. And so I can write this 1 by inserting a complete set of states. But now you can also see that if I write out this inner product now in the way it's defined as an integral over Teichmüller space, then this integral becomes, well, it's the conformal block times the conformal block bar times the OPE density of states times this and everything integrated over P, and then times the time-like Liouville correlation function times the ghosts. And of course, this by definition just is the conformal block expansion of the space-like Liouville correlation function. So it becomes this object. And now nicely, as it had to happen, because we're dividing out by the mapping class group, this object here is actually invariant under crossing transformations. So because we landed under Liouville conformal, the Liouville correlator and the time-like Liouville correlator, both are invariant under crossing. And so what this dividing by the mapping class group is doing is reducing this Teichmüller space back to ordinary moduli space. And so this number of conformal blocks that are invariant under the mapping class group, in some sense, should be the string amplitude that we're trying to compute. Okay, so this involves some sleight of hand, but let's try to think of this number of conformal blocks in a different way, namely by doing quantization. So the space of conformal blocks, where this came from is by quantizing a phase space. And this phase space is the moduli space of Riemann surfaces itself. And so that tells you that this number of conformal blocks is the number of the dimension of the Hilbert space that you're getting by doing geometric quantization on this moduli space of Riemann surfaces. And sort of happily, this moduli space of Riemann surfaces is a Kähler manifold, which means that you can simply compute this dimension by using an index theorem. And so the index theorem is this Hirzebruch-Riemann-Roch index theorem. And it tells you that the dimension that you're getting by doing geometric quantization is given by doing the Todd class, which is some particular characteristic class of this moduli space, times the exponential of the first Chern class of the line bundle. So this thing in the exponential is just the cohomology class of the symplectic form on this phase space. And you can express it in terms of sort of standard cohomology classes. If you know about cohomology classes on the moduli space, there's basically a degree 2 cohomology class called kappa 1, which is you can think of the Weil-Petersen form without any external punctures. And then are these psi classes that also appear in this Weil-Petersen form. So you can work out that the cohomology class of this Weil-Petersen form is this combination. And then by doing this integral, and using the index theorem, you're computing this dimension of the Hilbert space again. Okay, hopefully that step was not too crazy. But so we now know that the string amplitude is equal to this number of conformal blocks, but is also, and the number of conformal blocks is computed by this index theorem. So the string amplitude should be equal to this intersection number on modular space. So the nice thing on the right-hand side, this is now a purely cohomological formula, whereas on the left-hand side, it was a very explicit integral over modular space. And once you know what the right-hand side, it's kind of becomes standard mathematics.
I'm sorry, can you give some more comments on why we use Todd class on M without bar?
Yeah, thanks. That's a good question. Right. So, and that was, yeah, so, okay, the question is like the Todd class depends whether I take modular space or which compactification of modular space I'm taking. I don't have a particularly good answer to this. Maybe you have a better answer actually than I do. But so when we started, when we did this kind of derivation, then what we got is we just divided by the order of the modular space, the order of the mapping class group. So I would have thought that if you do geometric quantization, you should take the Todd class of Teichmüller space formally. But of course, then you're talking about non-compact space, and maybe you can do some equivariant cohomology or something. But point is that you should not care about the boundary divisors of this Teichmüller space that come from dividing by modular space. I think this is why you get Todd class without any boundary divisors. This sort of more honest answer is that it will work and it will all pass all consistency checks that we did. But yeah, I don't have a particularly good answer why it should not be compactification.
Okay, thanks.
Thanks. Great. And then once you know this, it kind of becomes standard math to make this Todd class more explicit. In particular, you can use this Grothendieck-Riemann-Roch theorem to rewrite it in terms of the standard classes on modular space. And you get a piece from this exponential, and then you get more pieces from rewriting this Todd class. And if, as Igor was asking, the fact that this is just a Todd class of M and not of some compactification implies that there are no boundary classes. Otherwise, you would have some boundary classes here also. Good. And once you're at this point, you kind of are happy because now you can just go and ask your favorite program to compute intersection numbers. And in particular, you already see that from this, that the answer would just be polynomials in these pi squares. So from the original definition of Liouville theory, it was not at all clear that the answer could have been a ridiculously complicated function. But here you just see that you get polynomials. It's very simple. And in particular, also, once you have an answer like this, you can you're guaranteed by using general theorems that you can recursively compute these volumes. So let me tell you about some properties. So I already mentioned that these quantum volumes, even though they were defined using this DOCZ formula and so on in the beginning, they turn out to be just polynomials. in the center charge, and these pi squares of degree equal to the dimension of modular space. They also have another interesting property that is not so obvious from the worksheet, is that you can kind of swap the roles of space-like and time-like Liouville theory. So what this means is you can send B to IB and P to IP, which is the same as sending the center charge to 26 minus the center charge and the conformal weight to 1 minus the conformal weight. And these volumes will essentially stay invariant up to a sign. I don't have a particularly good explanation from the worksheet why this happens, because sending C to 26 minus C throws you out of the allowed region of center charges that you could cover from the worksheet. Great. So yeah, so this derivation was not fully convincing, but so let me perform now some checks and discuss some further properties. So the simplest check is that the quantum volume, and now hopefully quantum volume, this word makes sense because it's the quantized volume of.
I'm very sorry. Could you repeat this previous remark about central charges?
Yes.
You say that you cannot just think that you replace matter and gravity Liouville theories just among themselves, yeah?
Yeah, right. You cannot exchange them because the matter theory is only defined for center charge less than 1, and the gravity theory, the gravitational one, is only defined for center charge bigger than 1. So if you send center charge to 26 minus the center charge, you destroy this condition.
So it's just sort of contradicts that one theory cannot be thought as continuation of another because of the.
Yeah. So yeah, what it means is you cannot define an analytic. So this answer turns out to be analytic in central charge in particular, whereas the worksheet answers are not analytic in the center charge. You cannot analytically continue the integrand to this region where center charge that C is less than 1, let's say. But you can analytically continue the integral.
Thank you.
Sorry, but you can let you continue both time-like and space-like theories to complex central charge, right?
That's right. Yes, that's right.
So I guess in this, apart from the real line, this duality kind of might make sense.
Yes, I think it does. Yes.
Okay.
Yeah, so maybe you can understand this this property for complex center charges, I think. But it's still not obvious from the worksheet why that will be true. Great. Yeah, so if you plug in the simplest cases, like the 3-punctured sphere, you just get 1. And you can immediately see from the worksheet that is true because the structure constant of space-like and time-like Liouville theory cancel. I told you the time-like Liouville structure constant is 1 over the space-like one. For the 4-punctured sphere and for the 1-punctured torus, you get a polynomial of degree 1 in the squares of the momenta. And I think it's kind of absurdly simple because the origin was quite complicated. We took these DOCZ formulas and times conformal blocks that don't have closed forms, conformal blocks, and you integrate them. So it's kind of nice. Also, there was also a question before, there's also a limit where this reduces to JT gravity, so just divide Peterson volumes. This is a similar property that happens for the 2, P minimal string, where they were investigated a lot by Artemev. And so in this limit, you scale this B parameter to 0, and at the same time you scale the P's such that this product B times P stays constant, and it becomes the geodesic length that you have in the Weil-Petersen volumes. Up to some normalization, though it's not really relevant. To convince you that it's true, we also did some numerics, so you can implement this worksheet integrand numerically, and by doing conformal blocks, and you integrate it numerically, and you can see that it fits pretty well. For like technical reasons, it was simple for us to evaluate the answer 1b as like a square root, some number. Okay, And so let me finally come to the matrix integral, but in some sense, this is an afterthought, because once you know that there's this intersection formula, you know that there's a topological recursion, and you also know that there's a matrix model description. And one way to specify the matrix model is in terms of its leading density of states. So the density of states at large n. And it takes this form of this sinh 2 pi b squared root e, sinh times sinh of 2 pi b inverse squared of e. And what's kind of nice about this formula is, first of all, if you replace E by P squared, because the energy you should think of as being the conformal weight, and the conformal weight was something like C minus 1 over 24 plus P squared. So if you replace E by P squared, the constant doesn't really matter. This becomes sinh 2 pi B P, sinh 2 pi B inverse P. And this is the natural measure. This is actually the Plancherel measure of the Virasoro group. So it's the natural measure that you get by Harish-Chandra, or Plancherel measure that you get. And this is also the universal density of states for high temperature that you get from Cardy formula. So another way of saying the same thing is that if you compute a disk partition function, and I haven't really told you how to compute partition functions with asymptotic boundaries. So far I only talked about partition functions on some closed Riemann surfaces, but you can also do this disk partition function. Then what it becomes is the Virasoro vacuum character on the boundary. So the boundary is a circle, and the circle has some beta associated to it. And the beta, and you can, if you compute the answer, it will be some function of this beta. And it turns out to be the Virasoro vacuum character. If you know about quantization, you can see where this comes from. This comes from because the answer on some general Riemann surface comes from quantizing the corresponding moduli space. And the moduli space that is relevant for the disk is so-called universal Teichmüller space. And if you quantize the universal Teichmüller space, you get the Virasoro vacuum representation. And that's sort of explains the name, why we call it the Virasoro matrix, the Virasoro string. Okay, and then how these matrix models work is that you compute these resolvents. So the resolvents are the expectation values of these objects, the 1 over some numbers minus the Hamiltonian. And I'm thinking of this matrix, this Hamiltonian, as the matrix I'm integrating over. You can also just think of it as a matrix. And all of those admit the connected components of this admit genus expansions, and those genus expansions, these resolvents in turn are related to the worldsheet quantities that you're computing. You can also relate those to the cases where you have these asymptotic boundaries, then you would have these partition functions depending on beta, but all of these things are some integral transforms of each other, so they're kind of simple to translate. So in particular, these partition functions, depending on the betas, you can think of them as being computed from knowing the quantum volumes, and then you glue these sort of asymptotic trumpets to it. So this is the language of Sachin or Stanford. But again, that only amounts to integral transforms. Sort of the non-trivial thing is that there's this recursion on the resolvents, and you can translate to recursion on the partition functions or the volumes, whatever you prefer. And I translated here to recursion on the volumes. And this is the analog of the Mirzakhani recursion relation for Weil-Petersen volumes. So in particular, if you take the limit of this recursion that I'm about to explain you, where the central charge goes to 0, this reduces to the Mirzakhani recursion relation. This is just one way of saying what topological recursion is. All of these formulations are equivalent. And how this works is that if you want to compute this quantum volume for some surface where you figure some G and N, then you single out one of the boundaries, P1. So this only works if there's at least one boundary, but there's also a way to cover the case with no boundary. And boundary, I'm thinking of a puncture now as a boundary. Because in the limit, in this classical limit, this reduces to a geodesic boundary. And then how you get the answer is recursively by, on the right-hand side, removing all possible 3 whole spheres. There are essentially 3 topologically different ways of doing this. you can remove a three-hole sphere containing this one special boundary by doing something like this. And then the resulting surface has genus one less. So what appears here is the surface where you have one less genus, but one more puncture or one more boundary. You have to integrate over the P here and the P prime here. And there are some particular measure to do this. You also have the case where if you have this three-hole sphere, it cuts the surface into two parts, and there are combinatorially several different ways of doing this, depending which p's land on which side, which is the sum. And you have to take the product of the volumes on the left and the right side. And finally, there's also the case where the three-hole sphere bounds also another external boundary like this, and then you have to sum of all these possible boundaries. Right, and the only sort of so this is completely generic in some sense. The non-trivial thing that's model dependent is what this function h is that defines this measure. You see this function h, it's, I don't know a closed form, but it has this integral representation. And this is the only place where this b enters, what the central charge is.
Sorry, Lawrence, I have a question.
Yeah.
Is it obvious that this h maps polynomials to polynomials?
No, it's not obvious. It's true, but it's not obvious. Yeah. Even in Mirzakhani's formula, it's not at all obvious.
Yeah, but here even less obvious. I see.
It's maybe even less so, yeah.
Mm-hmm.
But yeah, you can show that it does by like doing some contour manipulation. So in fact, like the efficient way of implementing this, we kind of implement this in the program is not in evaluating these integrals explicitly. Yeah. Right. But yeah, that's sort of the final point that you can. So originally these were defined as some string amplitudes, but yeah, you can sort of derive this recursion relation by doing the detour to the topological recursion. I would love for there to be a more direct derivation of this fact. So maybe, I mean, there's this ground ring that someone already asked about, way of evaluating these amplitudes explicitly, but I don't know how it works here. So it would be cool to get the structure more directly. Good. Any other questions on this?
But by the way, is there a way to numerically confirm this for more than 4 points?
People in the literature have done 5 points and 2 points on the torus for other theories, like minimal string. No, sorry, seek to 1 string has been done. So I think we could, but we haven't done 5 point or 2 point on the torus. But everything beyond is kind of impossible.
Yeah.
And there are already the errors like around 1% was the best they could do. Good. Yeah, I don't know whether I will have enough time to go through all of this. You should tell me when to shut up. But if there's no protest, I'll go on. And now talk about this complex Liouville string. And it's very similar, but remember that we defined it by coupling these two complex conjugated, and now these are ordinary Liouville conformal field theories to each other. Good. And well, there will be 2 very similar slides as before. So the worldsheet theory is kind of non-perturbatively defined by its conformal field theory. So again, the central charge takes this form. Now it's just space-like Liouville theory. You should notice that the condition that central charge is 13 plus imaginary is also something nice. It tells you that b squared is purely imaginary. Before we had b squared purely real. It was for the 2 theories, but now b squared is purely imaginary. So in particular, b has this funny e to the pi I over 4 phase. The spectrum is still the same as before, but now the C is complex, so we'll also take this little p to be complex. And it's kind of convenient but annoying to do this change of notation where we don't talk about this capital P, but little p, and the difference is just that the little p is I times capital P. But if you don't, I mean, you won't even notice if I'm not telling you. And there's still the DOCC formula. Good. That's what I just told you, that the central charge being 13 plus imaginary means that P is in this range. And also, it's nice to take P to be in this range, because then the conformal weight is 1 plus imaginary. 1/2 plus imaginary. And what that means is that if you construct on-shell vertex operators like this, then you can really think of the second vertex operator as being complex conjugate of the first vertex operator, because then it's on-shell automatically, because then 1/2 plus imaginary plus its complex conjugate is 1. And in particular, that means that the integrand, in this case, if you make this choice, is a mod squared. It's just the mod squared of Liouville theory of the central charge. In this case, it's also convenient, but again, not super important, that we include this lag factor. So we do this integral, but we normalize all the vertex operators in a slightly different way. Not super important. The important thing is, again, that we make it, this is an absolutely convergent integral over moduli space. And we want to figure out what it is. It's also, it has various kind of obvious symmetries. Maybe the least obvious one is that I can send B to IB and P to IP, which will exchange the two Liouville theories, because now they're on completely the same footing. So this will be the same property as that I mentioned before. Was kind of surprising that the answer was invariant under the sending central charge to 26 minus central charge, because it did not make sense. Now it makes perfect sense, and that's this condition that the answer is invariant under this replacement. Okay. So now it's kind of why I wanted to talk about both of these theories, is that now I don't know a derivation like in the other case. I don't know how to think of this as some inner product. So we did something very different. What we did is sort of to bootstrap the answer. And let me already point out that the answer will be much more complicated, because if you compute, for example, the 3-point function, before it canceled out between the two theories. But now it will be product of the DOZZ formula with the DOZZ formula, where you replace B by this minus IB and P by IP. And for some appropriate lag factor, you can compute this. And it was actually pointed out by Zamolodchikov some time ago. And one way of representing the result is as this infinite series. Notice this infinite series is very rapidly convergent because this B squared was imaginary. So this denominator behaves like a sinh. Okay, so that's the answer, but it's much more complicated than one, what we got before. But you can notice that it's an infinite sum over things that factorize divided by something also only depending on m. So that's why this representation is nice, and it will generalize to a higher number of boundaries. And so now, in general, what we do is, in this case, we don't have any good argument. So what we do is just to try to bootstrap or constrain the answer as much as possible. So one big advantage that we have is that the answer will be an analytic function in P. So even though we initially defined this thing to be only defined to be when P is in e to the pi I over 4 times real, so when that was a special form, we can, in principle, define and compute this for any P. And well, for any P, we have to be careful because this is not always convergent, but there's an analytic continuation. And so what we have is an analytic function, all these P's. Whereas for the minimal string, you just get a bunch of numbers and there's no obvious analytic structure. So what we will do is to use all this analytic structure that we have, as well as all the symmetries that we have, together with some explicit results and some numerics to try to get the answer. So some of the analytic structure is kind of obvious, namely these Liouville correlators, they have a bunch of poles, and these poles before in this Virasoro minimal string, they canceled out kind of miraculously. Now they do not cancel out, and the answer will have a bunch of poles. We'll also have discontinuities, and these discontinuities are associated to values of P that are outside of the spectrum because we analytically continued, where this integral ceases to converge. So now once we start analytically continuing, then it can happen that this modular space is no longer convergent, and then we get discontinuities in the answer. There are also more constraints. There are other symmetries. there are these high equation of motion that someone asked about before that impose some constraints here. But let me mention that they don't fully give you the result, contrary to the minimal string, because there are these ground ring operators, and the ground ring operators are only exist for degenerate conformal weights, whereas here we take the conformal weights to be continuous. So roughly speaking, they tell you what happens when you put one of the p's to some special degenerate value, but that doesn't tell you what happens for any p. There's also other properties, like there's an SOH, duality symmetry, that comes, you can explain from AGT correspondence and other things. So basically we put in all these things that we know about the answer. And we bootstrap it, and it turns out that there's once you know all these things, and you make some kind of you make an assumption essentially that the answer is not growing too fast. If you make one of these p's large, you get a unique answer. So there's a very natural solution to this conditions. And again, this is not rigorous. It's a conjecture that this is the answer. So I put again the danger. And so I'll tell you the answer now, what happens. And it's more complicated as in the BMS, in this Verzo minimal string. And the answer will be given by summing over degenerations of the worldsheet. So mathematicians call this sum over stable graphs. And the vertex that appears is precisely the quantum volume that we discussed before. So let me tell you concretely how it works. So if you take full punctured sphere, what's the answer? There's basically two different stable graphs. There's the trivial stable graph where you're not degenerated in the worldsheet, or there's a stable graph where you pinch the cycle for the full punctured sphere. There are also two permutations of those where you pinch other cycles. And for each of those, you have to associate a positive integer to every of the vertices. So in terms of in mathematics, this is called colored stable graphs. So they can have different colors, and you're summing over all these colors. And then for every external puncture, there's some sign factor. So this is basically just a normalization of the external puncture that's convenient. But more importantly, for every vertex, you get a vertex factor that is this Verzo minimal string quantum volume that we looked at before. And it also comes with some normalization. Yeah, and here you have the 0, 3 and 0, 3. Of course, those are 1, but I'm just writing it for clarity. And then there's also, when you have a puncture in the middle, then there's some momentum associated to it, and you have to integrate over it, which also comes with the sign that you have also here. And once you do all of this, this is supposed to be the answer. Let me just give you one more example. If you compute A11, then also there are two terms. One comes from the stable graph that describe a non-degenerate Riemann surface, and one stable graph where you pinch one of the cycles. And here again, the vertex comes with this V11, and here comes with V03, and here comes with an integral over a momentum Q. This also comes with a factor of 1/2 because this graph has an automorphism symmetry for the two. So this is probably a bit quick, but hopefully the structure is roughly clear. So this just comes out of this bootstrap. And then what we do is to just do many checks. So again, we check numerically that this function does the correct thing. So this is on the original spectrum for some random values of p. We can also do it when they're outside this spectrum, then the answer is no longer real. So there's an imaginary part also. And it matches very nicely. Let me type this. Yeah, and we also do other checks, like there are all these like analytic requirements, like this dilaton equation, string equation, and all these kind of things. So these things work out, but we don't have complete proof that it works. Good. Yeah, so I should finish soon. So let me just tell you this. So once you know this, again, essentially you win because you have a closed form expression for any genus and any number of punctures. So it's just a matter of using theorems in the literature to translate this to topological recursion and matrix integrals. And in this case, you translate it to a double-scaled matrix integral. And it's double-scaled because, well, for the experts, if you write down the spectral curve, it's not a hyperelliptic surface. So if it's a one matrix model, the spectral curve has to be a hyperelliptic surface, but in this case, it's not. That's why you need at least a two matrix model to realize such a spectral curve. In other words, if you write down the leading density of states of leading density of eigenvalues of one of the matrices, it takes this form. So it's again like sine of arc cosh. It looks similar to the minimal string, but this but the monodromies of this answer are not square root monodromies. They're more complicated. Right, and so the spectral curve, it's kind of a proxy that goes into the topological recursion. And so I'll tell you in a moment again what this recursion means in terms of the string amplitudes. And in particular, this curve, it has infinite genus or infinitely many nodal singularities. It's a non-compact curve and it has also infinitely many branch points. So it goes outside a little bit of what one usually does in topological recursion, where you have some finite number of branch points. And also in the topological recursion, then you get the sum over the number of branch points. And so you might wonder about convergence and so on. And it turns out that everything converges absolutely. And so I think topological recursion is still fine, but it's strictly speaking a little bit outside what usually happens. So finally, let me tell you that you can again translate everything to recursion of this AGN, of the string amplitudes. And actually, this recursion is exactly the same as what we had before for this Virasoro minimal string, except that, of course, that B now has a slightly different range. The only difference is that you also need to multiply by the 3-point function of the pair of pans that you're removing, because it's non-trivial. So before I didn't write it, but I could have written also V03 for this 3-point function that we're removing, but V03 was 1, so there's no point in writing it. So the only difference that you also have to write is A03 here. And so it obeys exactly the same recursion as the Virasoro minimal string. And the only difference is that the initial condition is different, that the 3-point function is different. But kind of remarkably, I think this function that appears in the recursion is exactly the same. Good. Any questions on this?
Sorry, I have a question.
Yep.
In principle, we can define a scalar product on the Liouville space using this imaginary Liouville measure, just the same as we did for the Virasoro minimal string. Do you have at least some guess what is the answer for this scalar product should be?
Yeah, I think it doesn't quite work, the scalar product, because the problem is that once the central charge is complex, and you complex conjugate the conformal block, you also complex conjugate the central charge, and then you cannot multiply by an object that only has real central charge. Right, you see, if you go back, sorry, here. Here you need to complex conjugate the conformal block. And so the central charge of this thing is the complex conjugate of the central charge of this thing. But both the left and the right moving central charge has to be equal to 26 in total. So there's nothing obvious you can write here. Yeah, so I don't. So you can write like a bilinear pairing or something like that, but it's not, will not be sesquilinear.
Okay.
Yeah. Yeah, this confused me for a long time. So if you have something good to say, I would be very happy. Very good. Okay. Yes. I have some further comments, but I think in view of time, I will just close. So let me jump this. Yeah, so the most important kind of summary that you should take away is that there are these kind of irrational cousins of that we call Virasoro minimal string and complex Liouville string. And these are pretty simple string theories. They're completely solvable. They both admit matrix model duals. In some sense, they're much nicer, mostly because they're analytic in all the quantities. And at least for this Virasoro minimal string, we sort of had a derivation of this duality. For complex Liouville string, it was also a derivation, I would say, but it's much more computational and less conceptual. So thanks a lot.
Thank you. Yeah, question, please.
Sorry, maybe it's not the question. I'm just curious what you think about it. Maybe it's a bit long also, so bear with me. So as you mentioned, I think, and also as we studied with Igor, so these three examples, like minimal string, VMS, and CLS, are kind of very simply related in terms of spectral curve. Basically, you need to do a reparametrization in some sense to reduce like the one form, omega 0, 1, from one theory to the other. And basically, well, there is a simple explanation for that, right? Because the disk partition function in all the three theories, when you have a Liouville plus something, it depends in the same way on the boundary cosmological constant. So that's why it kind of look the same. And the difference basically translates to the by differential and the branch points that you account for. So I was wondering if there is some way to maybe generalize this observation in the sense that this choice of parameterization seems to be the thing that defines what the matter theory we have in mind, right? Like, as for example, Seiberg and Schiff, right? They choose this parameterization as a sign of pi b squared s, because they have this what we call here by Seiberg-Schiff equivalence, which like equates different boundary conditions in this theory. So the more general question is, what do you think? Whether you think it can be generalized to a more general class of matter theories, and a more specific one is for complex Liouville string. How exactly would you guess this square root of z that appears in the spectral curve? From what data would you guess this matrix model?
Yeah, I mean, as you probably know, the square root is kind of an artifact, just that we only wanted a parameterization that is kind of only runs through the spectral curve once. Yeah, sorry. Where do I want to go? Sorry. Right. So the square root here, of course, you can remove and just put z and z. And as you pointed out, if B will be real, this is actually the same as the minimum model spectral curve. Except I'm not completely sure. So it's true that if you degenerate the spectral curve to the minimum model, or like to make B real, then it becomes a minimum model. I'm not aware of a simple relation of the objects that you get from like doing topological recursion on this spectral curve. If you take the limit of the resulting objects, they don't obviously converge to the objects you would get by doing topological recursion on the PQ minimal string spectral curve, just because the number of branch points jumps discontinuously. Also, like the recursion kernel jumps and so on. So I think in some sense, like if this limit, you can do this limit on this level of the spectral curve and it works. But I don't think you can do this limit in a simple way on the string amplitudes or the differentials. I tried for some time and it didn't work, but maybe you know how to do it.
Well, for 2, p case, I tried to do something recently. I think I wrote to you about it. So basically, in the representation for string amplitudes, you have, instead of integrals, you have the sum. This is kind of how it degenerates in a sense. But I was asking in this like context, like does this parameterization square root of z somehow also realize this some sort of Seiberg-Schiff equivalence in this theory? That makes sense.
Yeah, I don't know exactly, because I like to think of these boundary conditions as being somewhat abstract, because you can put like a boundary condition. I mean, you're right that corresponds to like the FCCT boundary condition. And Yeah, I'm not sure what.
Okay.
Yeah. Also, like, I'm not completely sure what kind of other meta theories you have in mind to put, like, when you ask how it generalizes.
Well, I mean, you could imagine like several possibilities. Just, I don't know, maybe a minimal model is not of the A series, maybe like a sum of two minimal models, like whatever.
Yeah. Okay. Yeah.
I
Yeah. I
mean,
think, yeah. Yeah. Sum of two minimum models. Yeah.
and also, I wanted to ask you that you mentioned the examples of C equals 1.
Mhm.
So it always confused me. Why is this example so much different conceptually? Why do we talk about quantum mechanics in the sense instead of matrix interval? Do you have some?
Well, one thing is that that you probably know is if you take sec1 with compact time, then you can also sometimes talk about matrix models. But if it's non-compact, then I don't know of a way. And I mean, there's sort of, okay, the idea is that you have time translation. I mean, there's one isometry in the bulk. So in matrix models, you typically don't have such a symmetry corresponding to time translation. So that's maybe conceptual reason why you would not expect that there's a matrix integral. But yeah, I don't think it's excluded that there's a matrix model dual also of sec2 string theory. Not at all. In fact, I would kind of hope that one thing that I was thinking about, maybe you know some, is like that sec2 string in some sense also, like, I find it remarkable that all these theories obey the same recursion relation. So you might think that also sec2 string obeys the same recursion relation, maybe. Or and I mean, of course, the 3-point function is always different, but the recursion relation could be the same. And then if something like this is true, you could also fit it into a matrix integral, but maybe you have to do some additional, I mean, the momentum conservation is not something that naturally comes out of a matrix integral. So I have to put something on top maybe to get it. But yeah, I don't know.
Okay. Okay.
Thanks.
No, thanks. Other questions, please. I have a question about this function h. Do you expect it has some kind of geometric interpretation?
Yes, maybe one answer I can give to this is that one way of writing this is that it's the logarithmic derivative of the quantum Dal logarithm. So there's this Faddeev quantum Dal logarithm, and it appears in when you quantize Teichmüller space. Yeah, it's the logarithmic derivative of this. This is just an observation, but I don't know whether like you can in some sense derive. I mean, this suggests that maybe you can derive this from like some geometric or some kind of quantized derivation of Mirzakhani's derivation of the recursion relation. But yeah, I think it's not like strictly geometric. It needs to be something quantum.
Mm-hmm. Or others? Or if not, let's thank Lorentz again.
Thanks a lot.
Thanks a lot. So hopefully we'll keep in touch.